Hello, welcome everyone. Welcome back. It's a great pleasure to introduce our next speaker, Wojciech Zaremba. Wojciech is one of the founding researchers of OpenAI, where he leads the robotics team. He received his master's from Warsaw University and École Polytechnique in France in 2013, and then his PhD from New York University in 2015, working under Rob Fergus and Jan LeCun. During his PhD, Wojciech spent 1 year at Facebook AI Research and 1 year at Google Brain. His contributions include the discovery of adversarial examples, applying translation models to computer programs, improved training of GANs, and building the first neural Turing machines with discrete actions. His current work is dedicated towards the development of general-purpose robots. Please join me in welcoming Wojciech.
Thank you for inviting me here. It's a pleasure to speak for you. So first of all, what is actually OpenAI? So OpenAI is a non-profit organization whose purpose is to build safe AI that would benefit humans as a whole, and that actually extends to building also general-purpose robots. So we would like to build actually quite capable robots that they can solve plenty of tasks, and would like to actually ensure that this would be beneficial to humanity as a whole. So it's quite conceivable that the robotics in the default way, it will actually cause increase of inequality gap, or people will lose jobs. We have few ideas actually how these kind of things could be avoided, and as I said, the mission of OpenAI is to ensure good future for humans. So, I mean, if you guys have more ideas how to ensure such a future, let's speak. And OpenAI is actually quite well positioned to do it. We have great founding, we have a lot of compute power, we have extraordinary researchers and engineers, and also as non-profit organization, our agenda is quite clear. So first of all, what is actually general purpose robot? So in a sense, majority of robots out there are actually just for a single purpose. So Roomba is pretty good in cleaning apartments, but Roomba cannot play chess with you, or it's not good in driving a car. But human, for some reason, has actually quite generic capabilities. So human is able to do all these tasks. Therefore, it's a general purpose. So also, let's say Bender from Futurama is kind of a general purpose. It's a robot that can solve any new task. So we think that there are few components that have to be tackled in order to build general purpose robot. It might be not enough to tackle just these problems. So we think that we need actually quite diverse environments. It's not enough to train a model in single conditions. Within these environments, obviously we need complicated behaviors. And simultaneously, we need to be able at the very end to ask a robot to perform a task of our interest. So even if we would have a really capable robot that can solve tasks in diverse environments, and we wouldn't be able to ask the robot to do what we want, such a robot wouldn't be of a great use. So in a sense, that gives rise to three major questions. One is how to get rich, diverse data for robots. Second of all, how we can actually obtain complicated behaviors on robots. And third of all, how even to ask a robot to do what we would like the robot to do. So let me start with the first one. So one of the approaches is to collect data from physical robots. So at Google, Sergey and colleagues, they created a farm of arms. There were several other approaches, several other attempts as well, and it works very well on such tasks. Now the problem is that you are not getting sufficient diversity. So such a robot wouldn't be able, for instance, to grasp objects in the forest because it was never trained in the forest. In order to get data from a forest, you would have to put this huge arm on your back and go to a forest or to a waterfall or so. So in case of physical robots, even if you can afford the large number of them, it's not that easy to obtain sufficient diversity. So other approaches, they relied on simulation, and some of them, they tried to make simulation to be more realistic. Some of them, they first start off with a simulation and then fine-tune on the physical robot. And the third, most sophisticated or most complicated approach is to train a model to not be able to distinguish if data comes from a simulation or from a physical robot. So let's ask the overall kind of maybe naive question is, do we ever need real data? Maybe it's sufficient to actually do training in simulation and don't actually do any training on the real data. And to put it differently, maybe if there is sufficient variability of simulated data, then real data would end up looking like a simulation. So there was prior work like that in case of navigation. This is quadcopter flight. So Feresh and Sergey, they were able to generate high-quality scenes of corridors, and within these scenes they were training quadcopter to fly. They got quite amazing trajectories. And the question is if that's actually proper approach for the manipulation, and manipulation requires really high precision. And also how much of a work you have to put to make your data realistic. Do you have really to have amazing textures, or maybe it's enough to put any textures and the model would be able to learn to manipulate? And third of all, do we need even any real data? And so what we have done, we generated plenty of randomized scenes, and the scenes were randomized in terms of textures, lighting, and camera positions, but none of it is actually very realistic. So textures, they were either solid or maybe a checkboard or so, but they are not at all realistic. We trained convolutional neural network just from such images to predict location of object of interest. So that's the work by Josh Tobin and colleagues. And it turns out that we're able to deploy such a model on physical robot, and here the robot is able to detect spam, can of spam among other distractors, and is able to find the location like precisely enough to grasp it. The cool thing is that training here happened with a mesh of spam, but none of other objects was actually present at all during training. So as I asked before, do we even need any pre-training? Do we even need any real data? It turns out that in presence of sufficient amount of simulated data, as we increase amount of simulated data, there is actually no difference in performance between pre-trained model versus not. There is the increase in terms of number of textures help. The more textures, the better prediction. And here, what we achieved is around 1.5 centimeter, which is quite close to actually limit of what you can obtain. Like a single pixel thing is around half a centimeter. So it's quite clear that this approach can be further scaled. So we can use many more sensors than a single camera. We can use plenty of cameras, depth cameras, and so we can arbitrarily randomize our scenes. We can provide, we can create way more sophisticated tasks. So under such assumption, under the assumption that simulated data can be pretty good proxy for the real data, we are asking second question, which is how to obtain complex behaviors on robots. And as we know, or let's say to some extent, it's to be determined when the methods break, but we have seen that if we randomize simulator, we can learn quite complicated behaviors. So the question is, as we have access to simulator, which means that we can query it millions of times, what's the way to obtain very complicated behaviors or interesting behaviors on robots? So one of the approaches is reinforcement learning, and turns out that reinforcement learning actually is not that fast. So we can, it's possible to obtain extremely interesting behaviors, but the training itself takes a while. So like Atari results, initial results, the training time was around 1 week. Of course, we would like our robot to perform way more complicated tasks, and training should take less time. So one of the answers is you can parallelize your training, and that's what people extensively do in reinforcement learning. So one of the approaches is called Gorilla from DeepMind. Another one, which is quite famous, is called A3C. And it turns out that, let's say, Gorilla is a very successful approach, but it's actually extremely complicated. It's not the work for a single person to implement it over the night. And one of the major reasons why actually reinforcement learning has some speed limit is actually to the communication bandwidth. So you can have multiple workers trying to solve a given problem, but at the end, they have to synchronize the vector of parameters with each other. And in a sense, you can provide more computers, but there is a limit in terms of the communication. So is it actually necessary to communicate all parameters at all? And at OpenAI, we came out with algorithm, which might sound actually extremely naive, that it's very that can be arbitrarily well parallelized. So the algorithm is called evolution strategies. You start with your set of parameters, you perturb them randomly, you check which results gave you an improvement, and you move in that direction. So algorithm even doesn't require gradients. So in case of classical reinforcement learning, you start with actions coming from the model, and you perturb them, you add noise to actions. And in case of evolution, actually, you perturb parameters. And in case of RL, you have to communicate either gradients or latest parameters. And that's what causes the bottleneck. And it turns out that in case of evolution, you can communicate just the reward and the seed of perturbation. So the communication is pretty much free. You can put a large number of computers, like in thousands, and the entire communication is in terms of scalars, which is reward and seed. So you can think, okay, neural network has so many parameters, like millions of parameters. How could it be even possible that you can sample in this space and make some reasonable improvement? And the algorithm that I just suggested, that's pretty much like it's pretty much hill climbing. So you would expect that there is no way for such algorithm to actually scale to so complicated tasks. And actually, it turns out that such algorithm is competitive with the state-of-the-art, the best reinforcement learning algorithms on the standard benchmarks. So we're able to, on Atari games, on 50% of Atari games from that DeepMind consider, we have superior results, 50% slightly worse results. So more or less, we are matching the performance here. These are the movies of how our network plays. In case of A3C, I mean, there was quite a lot of work in parallelization, so I think that even the training time of 1 day might be inaccurate to say that the current training in case of A3C takes 1 day on Atari. But the thing about evolution is that the algorithm is so simple that one of people from OpenAI within a weekend were able to write the parallel version of algorithm that distributes over a large number of cores. So in this case, it's 720 cores, which gives us 1 hour of training on Atari to match the results. Evolution itself is less data efficient, but it's actually just 3 to 10 times. So people are expected that if you don't have any gradient information, that might be by the factor of 1,000. It doesn't require any backward pass, which also opens a gate for the specialized hardware that is actually designed just for inference. So you can use the hardware that is designed just for the inference. In case of Mujoko, similarly, we're able to match the performance of state-of-the-art algorithms. And we're able pretty much to get from 1 day of training. So I remember when we have started OpenAI, John Schulman showed me his algorithm TRPO, and it was taking pretty much 12 hours on humanoid to train it. And there were like multiple attempts to run it, to speed it up. So we even had at some point people working for several months actually to optimize to run these algorithms in parallel. And right now, in case of evolution strategies, implementations that we can obtain, the trivial implementations that take, let's say, 2 days of coding, they can actually achieve the same results in 10 minutes of training. I actually believe that we can go down even further. So main issue is how to provision more machines, but I think it will be resolved by engineers at OpenAI. Cool thing is that algorithm actually scales linearly. So we start with 18 cores. The training time is over 600 minutes. We increase number of machines by 10 or so, and linearly we have a speed up in terms of training. So you can kind of ask how it's even possible that the evolution strategy works so well in the presence of millions of parameters. And one justification, what we believe, is that the dimensionality of intrinsic space is way smaller. So you can imagine that the parameter space has millions of parameters, but in reality, the manifold of where the things are really happening is way smaller. So all these other parameters that actually do not participate in computation are automatically ignored by evolution. And the evolution itself, people came out with algorithm over 30 years ago. There are entire journals devoted to evolution. But people in neural network or in deep learning community, they were not considering this research, let's say, highly enough to apply. That it turns out to be extremely valuable. So our contribution was actually to show that evolution strategy is competitive with contemporary reinforcement learning algorithms, and also to notice that actually it scales so well. So as I mentioned, our answer to the how to obtain plenty of data is essentially through randomizing various things in the simulator, and that seems to work extremely well, at least on the simplified manipulation task as we consider, on, let's say, grasping task. We'll see what are the limits. It's possible that it's gonna break. We can obtain complex behaviors extremely fast by using evolution. We think that's one of the approaches that can decrease iteration cycle. And as I mentioned, the remaining question for me, which is a kind of a fundamental question, is, let's say we have a robot that can solve various tasks. How even to ask a robot to solve something that is of our interest? So one of the approaches would be to speak to a robot, to tell a robot what we would like the robot to do, but it has some fundamental limits. So robot could just solve tasks that involve words that the robot is familiar with. So let's say if you would ask a robot, please prepare scrambled eggs, it would require a robot in advance to actually know what does it mean scrambled, what does it mean eggs. It might maybe look up at Wikipedia scrambled eggs, like how the things are connected, but somehow the knowledge about the task itself or the details of it have to be at some point conveyed, and language might be not sufficient. So we are saying that the one alternative is to show the task, and there are like various approaches like that. So Peter, during his PhD, he worked on autonomous helicopter flights, and they were providing various demonstrations to replicate the behavior of flipping upside down helicopter or doing various barrels. Similarly, John Schulman et al., they were working on not tying, and there was also some work on learning from demonstrations to obtain superhuman performance in surgical tasks. So one of the main things, common themes for the previous work, is that actually they propose various imitation learning algorithms, and according to this algorithm they learn from multiple demonstrations. And we actually suggest something one level of abstraction higher. We are saying we would like to learn imitation algorithm that imitates based on the single demonstration. So it's possible maybe to inject so much knowledge to a model that after training, it requires just a single sample to replicate behavior. So let's say, for instance, every human has sufficient knowledge that I'm able, without words, just to present the task and ask someone to do something. I can, for instance, do this task and ask anyone in the audience to repeat the task, and people will be able to replicate it without tens of data samples. So the setup, more or less, to be more concrete, is we would like a neural network to consume a demonstration. So here is a demonstration of someone opening a bottle, together with some other bottle in some different state, and it should produce an action that corresponds to opening this other bottle. Or the same neural network should be able to consume a sequence showing how to scramble eggs and a new situation, which is a pan, and it should produce an action that corresponds to preparing eggs on this new pan. So that's more or less the idea. And the algorithm, and I will show in a second what's the instantiation, what we're able to achieve. So we are not applying it to opening a bottle. We wish to do it in the future. But the idea is you sample a task, the way how the training works. You sample a task, you sample input demonstration, that's the demonstration that the network would consume. You sample a target demonstration from the task, in that these are very different conditions, and you make network to consume input demonstration and try to predict target demonstration. So that's the training procedure. And in our case, so that's the work by Rocky Duan. The demonstrations, they were involving stacking blocks in various configurations, and our model was able to learn how to replicate this behavior, how to replicate the final layout of the blocks. And the only way, in the sense, here, for instance, here the task is to build 2 towers of size 2. Here there is a task to build 3 towers of size 2. And the network with a single instance of an input trajectory is able to learn to replicate the task. I will be more concrete in a second. So the tasks, as I mentioned, are to obtain some final layout. And in this case, the layout for this task would be, that's the tower of size 4 having blocks A, B, C, D. Here is example of another task or another layout. There are 2 towers of size 3 and 1 tower of size 2. And in our case, the data set, the tasks that we consider, they involve from 2 to 10 blocks. There are 183 distinctive layouts after removing all equivalent permutations. And we have a split in terms of what are the tasks for training and on what task we'll be evaluating. So that's actually quite important. In case of classical reinforcement learning, there is no difference between training and testing. You are testing on the same task that you are training, but here we would like to train network to be able to imitate, to replicate behavior. So ideally, if the task would be way more involved, we would like to obtain behavior that it was never trained to scramble eggs. You just record scramble eggs, is the file saved on the robot, and you can press the button to evoke behavior related to given recording, and that should replicate scrambling eggs in very different kitchen or so. But as I'm saying, our setup is pretty much a proof of concept. So the cool part about the performance of our network is that it's actually works with demonstration of a variable size. It works with extremely long demonstrations, and the sequence of actions is also extremely long. So our sequence of actions, they span something like 3,000 time steps, and it also works with variable number of blocks. Let me a little bit speak about the architecture. So as I mentioned, the demonstration comes in to the network together with the current state. Next, it turns out that in order to prevent overfitting, we have to drop randomly some of the time frames. If we don't do it, we actually end up overfitting. So during training, we drop some intermediate time frames. Then our network, our network is actually built to deal with blocks and objects. It's not based on vision. We have some attention that takes into consideration, kind of tries to look which blocks are close to each other. Then there is, let's say, attention over demonstration. So you could imagine it's like the demonstration is a video, you're watching a video, and then you're going back in demonstration to figure out which pieces are currently the most relevant. And after applying demonstration, we are getting fixed size embedding, and with attention that goes over the current blocks, we produce some hidden state that is mapped to action. So I'm gonna show video. Rocky showed it before. I will try to actually explain it more. So here at the left, that will be input demonstration, and the network first actually watches this entire demonstration before doing any action. And at the right, there is a policy that we obtain, and we'll see two attentions. So there is attention over demonstration, so it means that the network can focus on individual pieces of the demonstration. That's where the purple color or black color will occur here. There is like several heads for attention, and there is also attention over the current state. So initially it started looking at the block A. Let's see how it goes. So it looks at the block A, it starts looking at block B, so actually it moves also to block B. It starts looking at the block D, where it actually moves, and at the block E. Here at the input, you will see that it ends up building, let's see, so here this is a time axis. Here there are multiple heads. And we'll see that at the right we'll get the same outcome as at the left, even though the initial layout was very different. So here we achieved 2 blocks of size 3, 2 blocks of size 2, and at the right it achieves the same final configuration. So the cool part is that actually performance on the held out tasks. So as I mentioned, there was 183 tasks total, and 43 of them, they were held out. So we never actually trained on them. Our performance on the held out task is very similar as the performance of our demonstrations in the first place. So our demonstrations, they were not that great. If you move to actually large number of blocks, they were failing at some point. So our training data was not that great. And the network that we obtained through one-shot imitation actually matches pretty much the training performance, but it's on the held out tasks. So in a sense, today I spoke about 3 main topics that we think are quite important to obtain a general purpose robot. This is a way to obtain diverse data, the way to obtain complicated behaviors, and actually the way to tell the robot what's our intent. And of course, this still might have plenty of limitations. So so far, we haven't tried our tasks on our method on tasks such as cooking or cleaning, and I wish to actually move there. It's also we don't know when, so we are extensively using a simulator, and it's unclear if for harder tasks simulator has sufficient amount of fidelity. It's also the case that so far we're using parallel gripper, and we might want to move to robots with more complicated control. And I would say it's still many of these things are proof of concept. There were like plenty of people involved, and that's pretty much their work. And I would like to thank you for listening and thank to the team.
Hi, thank you for the talk. Evolutionary strategies have been extensively employed in both neural network and robotics for the last 40 years. And the reason why they have not been used, at least in robotics for real-world applications, is because typically they need impractical number of experiments. 10 million experiments is unrealistic on any robotic system. So I'm wondering, how do you plan to to transfer to the real world?
So as I said, I actually believe that it might be sufficient to train on large number of randomized simulations, and then real world starts to look like a simulation, and then our techniques actually might generalize to the real world. So in case of the first of our efforts, we have seen that training purely in simulation was sufficient to obtain excellent performance, but it might be the case that once we move to more complicated tasks, it won't be the case. You mentioned that evolution strategy was applied to neural networks, and it's true for extremely small neural networks. These are networks having 50 parameters, 100 parameters. So people were intentionally trying to make extremely small neural networks. It turns out that if you try to apply evolution strategies to vanilla networks as people considered them 10 years ago, actually evolution strategies also doesn't work. You have to add all the tricks that people developed with stochastic gradient optimizations, such as batch normalization and so on. And surprisingly, these tricks help evolution strategies as well.
Approaches like imitation have been used with networks with thousands or millions of parameters.
Evolution strategies?
Yeah.
Okay, I might be not as familiar. Yes?
You looked into extreme randomization for the physics. Have you looked into extreme randomization for the physics or the control part beyond just the perceptual part?
There is some effort like that at OpenAI, but I mean, still it's not that we can say much. So I mean, that's something that has to be done. Perception might be not that hard as, let's say, physics itself. We'll see what are the limits to it. Please.
Can you say something about adversarial, where you see the adversarial examples at this point, and where this might intersect with some of this new work?
In case of our training?
Yeah.
I mean, we have seen that clearly if you don't have sufficient amount of randomization, then your methods actually are overfitting. So it was extremely important to randomize camera or lightning. I wouldn't say these are adversarial examples. This is more that you are not covering sufficiently the space. Yeah, I wouldn't say that. I mean, in a sense, in case of adversarial examples, even when they are present, it's hard to determine that they are the cause of the problem. It's easy for us to generate adversarial examples and then see, oh, this is an adversarial example. But I haven't seen situation that in ImageNet training, someone can say, oh, in test data, this is adversarial example. We don't know if actually we are affected by it.
Okay, but I thought it was useful for like hard data mining, hard example mining, right? So that you can use that to further train. Do you try to use something like that here?
So
no?
Here we are just sufficiently randomizing. We are saying let's consider various degrees of variation. Let's consider lighting. Let's consider texture. Let's consider camera position. If you don't consider any of them, you end up if you skip one of them, you end up actually overfitting. It might be that your network is focused too much on some given feature. It might be still possible that there are some adversarial examples. We have seen situations that for some reason there is a pink block that we cannot detect well. And I don't know why. Maybe it's we need more randomization, but there is this property. For some reason, pink block was hard for us to detect, even though all others were really easy for us to detect.
Okay, so I guess what I'm getting at is that is there a systematic procedure for generating adversarial examples in this context, or
No.
is it, in general it's hard? You have to do it special case, right? There's not a general approach to generating adversaries.
No, we don't do anything special for adversarial examples.
All right, I think we're good. All right, thank you, Wojciech.
Thank you.